Alright, so we've talked about some common names for acids. We're going to talk today about the rules governing how you name those acids. Some acids have, like I say, common names. Some have just chemical names. Some of the more common ones will be known by the common name, but all acids can be named sort of according to IUPAC rules or just the general governing rules of naming compounds. And so let's talk about binary acids first of all. Binary, you should know what binary is. Bi means two. So we're talking about binary acids. We're talking about two elements. And one is going to be hydrogen, really, for pretty much all of these binary acids that we're going to talk about. And so HF is an example, and its name is hydrofluoric acid. And so in binary acids, they always begin with hydro. They always have hydro at the beginning, and that's, for the H sort of thing. You can think of this H as hydro, hydrogen, hydro. The stem of the name is whatever the other compound really is, okay? So if hydrogen is the positive cation in this compound, fluorine is the negative ion, and that's the anion. So if this is Cl, it's chloro, or chlor, and if it's I, it's iodo, or for iodine, or Br, whatever it is. That's the stem. And then ic at the end, IC at the end. So hydrofluoric, this is hydrochloric, hydroiodic. Okay, so there's the hydro, here's the iod for iodine. HBr would be hydrobromic, and so on. So it's usually, as you maybe noticed, a lot of these common ones are the halogens. Okay, so group 17 there, fluorine, chlorine, bromine, iodine, along with hydrogen. So that's where you'll see most of those binary. Questions? Okay, so we'll move on to ternary acids, so involving three elements. And I think all the examples we'll do are just three elements, ternary acids, and bases as well. So we'll go over the rules for those as well. So when we have more than two elements involved here, then the naming gets a little bit more complicated. And this is why I asked you to start memorizing the common acids and bases, because just looking at a formula and trying to remember some of these naming rules is a little bit tricky. Now, if you know some of these rules, as much of this body of knowledge as possible, then it's pretty easy to figure out the name. But if you start memorizing now, this will all make a little bit more sense. It'll be a little more automatic for you. So, generally the most common form, and this is why it's a bit complicated, because how do you know what's the most common form? Well, it's just the one that you see most often, or the one that's that's used most often, the one that's more readily abundant. So, the most common form of an acid has a suffix of ic. Okay, so we are going to have variations of the most common form. But an example here would be H2SO4. Okay, now that one you've all seen a number of times. That's a very common acid. It is sulfuric acid. All right, sulfuric. So the element that is not hydrogen or oxygen is sort of the stem of the name. So in this case, and we don't say hydro either. We don't say hydro at the beginning. That's just for binary. For this one, it's sulfur is the element in the middle here. So this is sulfuric acid. This one, we have hydrogen, oxygen, and kind of the middle one is chlorine, so that's chloric acid. Okay? Common names generally come from the element that is not hydrogen or oxygen. So that's where these names kind of come from, is the sulfur here and the chlorine. Okay? Now, this is where it gets a little bit complicated. If an acid is formed, and we're talking about, one of these common acid forms, if an acid is formed with one fewer oxygen, so that's the most common form, if it has one fewer oxygen, then the suffix, that's the kind of the naming part at the end, changes from "ic" to "us." And again, I can't stress it enough. Getting to know these, especially the common ones. Like, you got to memorize the common ones that I've suggested there before, and then it comes a little bit easier. Which one is the most common, H2SO4 or H2SO3? Well, you kind of just got to know that, right? So H2SO4 is the common one. So H2SO3, it's going to be sulfur or something. Well, the 4 is the "ic," the 3 is the "us." Okay, so if the common form of the acid is formed with one fewer oxygen, it changes to "us." If the most common form has one more oxygen, and again, you don't have to copy these notes word for word, just make your, jot notes or whoever you want to do that, but one fewer oxygen, suffix changes to "us. One more oxygen, okay, the suffix is the same, but the prefix is added, and it is "per." Okay, and where you'd find this, a more common form of this would be this example right here, HClO4. Remembering that HClO, I'm just going to back up for a second, HClO3, see that? That's chloric acid, right? That's the most common one. So HClO4 is one more oxygen, so you add the "per" in front. So it's perchloric acid. Perchloric. Okay, so just let's go over this, review this really quickly so far. The most common form just has an "ic" at the end, with the element that's not hydrogen or oxygen being the kind of the root or the stem of the name. So sulfuric chloric acid. A variation from that more common one with one fewer is "us." So this one would be sulfur-us instead of sulfuric. One more, there's a "per" that's added to the beginning. And finally here, if the form has two fewer oxygens than the common form, so two fewer oxygens, then we do two things: add a prefix hypo, as well as a suffix of "us." So HClO, all right. Remember that HClO3 is the most common form, and that is the "ic" suffix, right? HClO2, right? HClO2 is "us." HClO4, all right, is perchloric. And if we have two fewer, so that's HClO now, so here's the more common one, we have two fewer, then it's hypochlorous. And that will sort of be the extent of the naming rules that you're going to have to work with here. And you can look on page 579 as well here. There's a table 23.4 in your Merrill chemistry, 23.4, page 579. It gives you some examples and their names, and that's where these notes came from, so you can read in the textbook there about that. So just a little side note there too on page 579 in the textbook. As I've mentioned before, the very middle of the page there, first sentence in that paragraph under the table, it says, "It is not possible without previous knowledge to know which form of an acid is most common." So that's kind of why you just kind of got to learn the more common acids, you know, you got to know how many oxygens there are in sulfuric and chloric and iodic and stuff like that. Okay, so there's a few that you need to kind of memorize first, and then you can go from there with these rules. Okay, now also on the next page there, page 580, which we don't have notes on because we've already done this in this course, there's a little bit on naming organic acids and bases, which, you know, we've talked about that in our earlier organic chemistry section, right? The carboxylic acids and stuff like that. So we won't cover that here just now. But, okay, has everybody got these notes here? Yeah, okay. All right. So we're going to actually, let's see, I think we're going to move on a little bit here today because we have quite a bit more time in this class here. So these questions right now, you can jot these down. I don't want you to work on these right now. I'll give you some time at the end of the period to work on this. But page 580, number 9 to 13, is some practice on these naming the acids. So just jot that down. And instead of a homework assignment here, we're going to go over this in class, okay, the next little bit. So just you can jot. All right, so page 580 to 589, there's a few terms in there that we've already talked about, and Amphoteric is the one term that we've talked about already in there. So with these bold-faced terms there's a few that, one we've already talked about, and that is Amphoteric. Do you remember what that was? We talked about that yesterday. Yes, something, a substance can behave either as an acid or base, depending on what it's in solution with, and water is a good example there. So Amphoteric, also anhydrous is another word that you're going to need to know what that is. Anhydrous, and that simply means, if you look on page 582, okay, it means without water. So anhydrous is not water containing. So like that. Also on page 584, there's a chart, and that's kind of what we're leading to next, is the strengths of acids and bases. And so if you look at that chart, strengths of acids and bases, and maybe I'll bring one up here for you. All right, so you have a chart that looks something like this on page 584, and it's basically, this chart is an order of strengths of acids and bases. So as you go towards the top here, we have the strongest acids at the top, and you see in your chart that HCl is right up at the top here. H2SO4 would be right around that same. They're pretty much equal there. And down here, NaOH, very, very strong base, okay, as well as here's some other bases here. All right, so you don't have to memorize this, but what we're going to talk about next here is what are the numbers that are associated with strengths of acids and bases, and what are they called and how are they used. So, all right, so in introducing that, let's talk about this right here, Kw. We've talked about equilibrium constants, solubility constants, and now we're going to talk about a water constant. So Kw is something called the ionization product constant of water. Because water dissociates slightly and predictably into H+, and that's actually H3O+, and OH ions. Okay, now we may have talked about this before, I believe we have, but just in case we haven't, when we have a regular water molecule, H2O, if you have a sample of pure water, you don't have exclusively H2O molecules in there bumping around. Okay, water actually naturally dissociates very, very slightly, and really it's like it dissolves. Okay, it dissolves, it dissociates, it splits apart, and then those ions get back together, and this is happening on a very small scale all the time, even in a pure sample of water. And so that's what this first statement says. Water dissociates slightly and predictably into hydronium ions and hydroxide ions. So because that happens, there is a special solubility product constant for water, and that's what the Kw is. So once again, in any sample of pure water, you are going to have a predictable concentration of ions that make up water. So there are going to be some ions that are separate in solution, along with all the other water molecules. And so that's what Kw is. The value for Kw is 1 times 10 to the negative 14. Now, is that a pretty small number or a pretty large number? That's pretty small. Now, remember with our KSP chart, right? Anything that was under times 10 to the negative 4 or so, right around there, anything that was a smaller KSP than that, we said was generally insoluble, right? And times 10 to the negative 36 was some of them in there, and that's extremely insoluble, so they are not, going to dissolve. Water is sort of in between there. Water will dissolve slightly, but it's generally, if we want to call it, insoluble. So water is pretty stable in that water molecules, they won't just automatically break down into ions completely. It's pretty stable, and so it would generally be called an insoluble compound. So water is pretty safe, it'll stick together, but there are some ions in solution. So if we think about Kw as a special solubility product constant, then that means that the product of the concentrations of these ions right here will multiply together to give you 1 times 10 to the negative 14, always. And that's really important. That's really important, especially when we're talking about acids and bases, because, as you know, if an acid is introduced into solution, guess what's going to happen to this concentration? What's going to happen to that concentration? If an acid is introduced, so let's say HCl, okay? An acid is introduced to water. All right? So what is this? What are the products here when acid is introduced into water? Yeah, so it looks like this, right? H3O plus. Now, if an acid is introduced, there are lots of these that are produced. All right, so if we got a pure sample of water and we add some HCl, this concentration is going to skyrocket. It's going to go up because we're adding more of it. Because HCl is going to break down, right? Strong acid is going to fully dissociate. That's what a strong acid is. It splits apart really easily and very completely. And so this is going to spike up. So what's going to happen to these ions in solution? If this goes up, and I know I have a constant over here, so the product has to equal this. If this goes up, what's going to happen to the OH ions in that solution of water? Yeah, it's going to go down. So 2 ways you can think about this. If we have some of these ions in solution already, and you introduce more hydronium ions, they're going to bond with the hydroxide ions and form more water molecules, right? So this goes up, this goes down. That's one way you can think about it. The other way is that simply mathematically, if 2 numbers have to multiply to a certain number, and one of those numbers is changed to a larger number, the other one has to be smaller. Right? So if we have, 7 times 2 is 14, and this 7 actually goes up, to 14, what's this other number got to do? It's got to go down to 1. You see? That's basically what we're dealing with. If one number goes up, the other number has to go down to make this constant still a constant. You with me so far? Okay, I know this is super exciting stuff on a Friday morning. Yeah, first class, I know. This is like amazing. But if you guys, this is not hard stuff, I don't think, but it's new. So yeah, if you may have questions later. That's no problem. But this is really important because we talked about KQ, you know about that, right? We talked about KSP, you know about that. So this should be fairly straightforward. Okay, so let's just read on a little bit here. This value holds true even when, and this is what we just explained, so we'll formalize this in notes, even when acids or bases are added to the water. So the value, the Kw, that is, holds true, or is the same, because it's a constant, even when acids or bases are introduced or added to that water solution. And that's what I just explained, that constant it holds true. So if we add an acid, the hydronium ion is going to go up and the hydroxide ion is going to come down. We can use this expression to calculate concentrations of both hydronium and hydroxide ions, as well as calculating pH. So we can use this expression to calculate hydronium and hydroxide ion concentrations, as well as calculating pH. Yeah, small p, big H. The H is going to be in reference to hydrogen. So we have capital H because that's the symbol. And the P, which you'll find out, it represents the like a logarithm. It's like a mathematical operation. So that's why it's small. Not to be confused with phosphorus or something like that. Okay, so here's let's do this example right here. I've already done it for you. Let me walk you through it. What are the concentrations? This is what the question would look like. What are the concentrations of hydronium ions, so that's the H3O plus, and the hydroxide ions, that's the OH minus, in a pure sample of water? Any pure sample. We have nothing else in there. Pure sample of water. Okay? So water is going to break down to hydronium and hydroxide. Okay, we know that. And these are in a 1-to-1 ratio. That's pretty straightforward. You don't have to worry about that too over there. It's a balanced equation. You don't have to worry about that too. And so what we know is that these concentrations have to multiply to 1 times 10 to the negative 14. And so we know that really this is x times x, because they're both unknown. It's a 1-to-1 ratio. There's no exponents. You don't have to double anything or triple anything. And so it's basically just the square root of both sides gives you this number right here. And what that number is the concentration of each ion. So they're equal. Remember, 1-to-1 ratio. And their concentrations would be 1 times 10 to the negative 7. So my question is here, and I'm not going to reveal the answer to you right now, but here's the second question down below. Okay, here's question 2. If the OH concentration, the hydroxide concentration, changes to this number, 2.5 times 10 to the negative 9, what is the hydronium ion concentration? So now I want you to use your Kw, equation there, your statement, and solve for H3O plus. So answer this question number 2. Take a minute, answer this question number 2, and I'll reveal the answer to you in a second. All right, so to simply answer this question here, we have this statement, right? 1 times 10 to the negative 14 is the Kw, which is really the solubility product constant, or the product constant for the ions here of water. And so if we fill in the value here for the concentration of OH, and we solve for this by simply dividing, so you divide both sides by this number, you should get 4 times 10 to the negative 6. And remember that's moles per liter. Okay, it's always in concentration, moles per liter. And that should be your answer. You guys get that for an answer? Okay. All right, take a moment to turn to page 607 in your textbooks, skip ahead a bit, and we'll just talk a little bit about the pH scale. Okay, so here's a pH chart, similar to the one that you have in your textbook. There may be some things in your textbook that aren't on here, but we just take a look at this one here. So pH of 7, okay, the pH scale, all right, let's talk about the pH scale. this is a scale of measure of acidity, okay? Now here are some things that are on the pH scale, and as you see on the right side of the scale, and we won't talk about these numbers just yet, okay, I'll get that in a second, but on the right side of the scale, where the pH is high, nearing to 14, these are more basic things, okay? So NaOH, look at that. It is almost as basic as you can get. We know that's a very strong base. Bleach, ammonia, detergents, okay, soaps and detergents, stuff like that. Seawater, even blood is slightly basic, okay? Now pure water, should be noted, pure water right here, is right at pH 7. And below pH 7 are the more acidic substances, and that includes coffee. Now, what did we guess about coffee? Was it acidic or basic? Okay, we guessed basic. So coffee is actually acidic, and just ask me. I drink a lot of coffee. I have coffee stains in my teeth, and it's not good. And I'm going to the dentist in a couple of days to get all that scraped off. Isn't that a nice thought? For my cleaning. But yeah, they always kind of look at my mouth and say, "Hey, you're a coffee drinker, aren't you?" I'm like, "Yes, I am." So, oh yeah, coffee and orange juice and like pop, Coke. Coke is really bad. Acidic, highly acidic. It'll eat away at your enamel. I knew a guy. I was in a band with a guy once that drank a 2-liter Coke every day, and yeah, his teeth were gone by the time our band split up. But anyways, yeah, it's terrible. Like it was awesome. Anyways, so now let's talk about the numbers. Okay, so where do these numbers come from? Hopefully you've talked about the pH scale before in other science classes, maybe math. Sort of, not really. That's fairly sad. But anyways, pH. Okay, so the measurement of acidity of substances, and this is where the numbers come from on the pH scale. Okay, 1 to 14. Basically, we're talking about the concentration of hydronium ion, or H+. You'll see it, you'll see H+ too in different, like even on this chart right here. But we're talking about the negative logarithm, all right, and some of you are in, math that you know about logarithms, okay? But the negative logarithm, and you can just punch that in your calculator, no problem, of the hydrogen ion or hydronium ion concentration. That's how you find pH. And on this chart, it's a good way to understand where that comes from. For example, a pH of, let's say coffee. Let's go back to coffee, okay? A pH of 5 means that the hydronium ion concentration is 1 times 10 to the negative 5. All right? So if we go over what logarithm means, for those of you that aren't familiar, logarithm is sort of a way to get the exponent of, in this case, base 10. It's the way to talk about that exponent. All right? So 10 is raised to what power? In this case, with coffee, okay, 10 is raised to the power of negative 5. You see negative 5 there? So logarithm means what exponent is this concentration raised to with a base 10? And coffee is raised to a power of negative 5. So when you add the negative in front of that, that negative 5 value becomes positive 5. Because it's a lot easier to deal with just regular old positive numbers than it is negative numbers. So a pH of 5 means that the hydronium ion concentration is 1 times 10 to the negative 5. That's what that means. Let's look at some others. Gastric juice. That sounds like a drink you might get at 7-Eleven. It's not. That's stomach acid. Okay? We talked about that too at the beginning of the introduction there too, a couple days ago. Yeah, if you order some gastric juice at your local restaurant, they'll look at you a little bit funny, and you don't want to do that. You actually could order that. Say, "I'd like some gastric juice, please." Because I don't think we have that in the menu. Say, "Actually, don't worry about it. I think I have some already." You can play a little chemistry joke, I know. Isn't that great? Probably do that, and they will walk away shaking their head. Unless they're a Chemistry 30 student, and then they'll get it. Right? Isn't that something that you would do at a restaurant? Can I order some gastric juice? Oh, forget it. Actually, I already have some right here. Okay. Anyways, gastric juice. Okay, what's the pH? Maybe about 1 point what? 1.3, let's say. Okay, pH of about 1.3. That is pretty acidic. Remember, low numbers on the pH scale, very, very acidic. So that means that the hydronium ion concentration of gastric juice I don't like that name actually, stomach acid, let's say that, is 1 times 10 to the power of negative 1 point, whatever we just said, 2. Okay? 10 to the negative 1.2. That's the concentration. On the other side of the scale, bleach. Okay? Bleach is about 10 to the negative 12.3, let's say. So here you got the concentration of hydrogen ions. Notice, okay, stay focused. Sorry, no more gastric juice discussion now. But notice that when you have something that's very basic, you have a very small concentration of hydrogen ion concentration. See that? Very small. You also have a very high concentration of OH minus ions. All right? So another thing I want you to notice is that these numbers right here, whatever they are, if it's 11 times 10 to the negative 11, that for hydrogen ion, that the hydroxide ion will be whatever number adds up to 14. So 11 and 3, 10 and 4, 9 and 5, 8, 6, 7, 7. See that? So the numbers, the corresponding numbers for concentrations here, these numbers will add up to 14. All right? Questions? Okay. So milk and blood are pretty close to being neutral, but slightly acidic, slightly basic. Okay. So it's interesting to note that milk is slightly acidic. I don't know if you know that or would have guessed that. Well, that's yeah. You thought milk was basic. Okay. Why would you think that? Well, I mean, I know that's what I would think too. Why would you think that? Because what? Do we ever use milk as to counteract acid? Right? You think that acid and base would be opposite, right? And so if you have an upset stomach, or you, I don't know, something that you have that's really spicy or seems really, acidic, you might take some milk to kind of settle things down, right? Well, milk is pretty neutral, okay? If you have really spicy wings at the restaurant, sometimes you have sour cream or something to counteract the spiciness, right? Well, sour cream is sort of a milk product. You might think milk is opposite of, not that wings are acidic, but question? Okay. All right. All right. So the pH, okay. Now think about this previous example that we just did here. Here's the concentration of hydronium ion. What is the pH? Okay, that's the question. What is the pH of this example? And if we were to do that, we know that pH right here is the negative logarithm of the hydronium ion concentration. And so that, in this case, is this number. So get on your calculators there and plug this number into your calculator. Negative logarithm 4 times 10 to the negative 6, or that's 0.00004. That's 5 zeros and a 4. And see what you get for a number. And it should look something like this up on the board here. Yes, this logarithm is base 10. So your calculator, if you bring a calculator up here, this log right here, okay, is, if there's no base written, it's understood to be 10. That's the common logarithm. All right, so we'll just do that here. Negative log 1, 2, 3, 4, 5, 4. That's going to be 5.39. So there we go, pH of about 5.4. Right? Okay. What time we got? Okay, we're in good time. Let me talk about just one more thing, and then I'll give you some time to work on your questions. And that one little thing is this right here. Just as there's a pH, there's also a pOH. And as you guessed it, the pOH is the negative logarithm of the hydroxide ion concentration. So pOH is the negative logarithm of the hydroxide ion concentration. So we usually talk about pH, not pOH, but it is a thing. not as common to refer to. But just like the products of the concentrations have to equal 10 to the negative 14. What this means is that the pH plus the pOH has to equal 14 always. So that is an important thing to remember. That pH plus pOH always has to equal 14. All right. Got that written down? Okay. So you wrote down those questions from earlier in the class. There's some questions here as well. So I'll give you the rest of the class, about 12 minutes or so, to work on those two sets of questions. And then we'll be looking at KA and KB tomorrow. Okay? So these questions here, try and get them all done for tomorrow. I'm not taking them in, so if you don't get them all done, that's fine. Yeah, whatever. Monday. Thank you. Yeah. No, come meet me here tomorrow morning and Saturday morning. Yeah, and we'll go over. Yeah. Okay. Next class. You know what I meant. Next class. Yeah. Thank you for clarifying. Just in case anyone thought I was asking you to, have these done for Saturday morning, I was going to check them or something. No. Yeah.